Baalbek, Lebanon, 1996. A German engineer named Friedrich Ragette walks up to a wall he has come to measure. Above him, resting inside the podium of an ancient Roman temple, sit 3 stone blocks. Each one weighs more than 800 metric tons. He looks at his equipment. He looks at the modern mobile crane parked in the distance, brought in for the site survey. And in his notes, later cited in the German archaeological literature, he writes something uncomfortable. No crane operating in the region that year could lift was already sitting quietly on that wall. Now hold that image, because a few hundred meters from where he was standing, in the same quarry the temple stones came from, an even bigger block was lying in the dirt. That one weighs close to 1,200 metric tons. It had been partly shaped, partly separated from the bedrock, and then simply abandoned. Somebody 2,000 years ago planned to move it. How is that possible? That is the question this video is going to sit inside for the next 40 minutes. Not was it aliens? Not was it Atlantis? A quieter, more uncomfortable question. What if, in specific places at specific moments, ancient builders knew how to do things that modern engineers, standing in front of the finished result, still cannot fully explain? According to reporting drawn from field surveys, peer-reviewed engineering journals, and the archaeological record itself, this pattern is not a single site. Is dozens of them. Baalbek in Lebanon, Puma Punku in the Andes of Bolivia, the unfinished obelisk of Aswan, the stone boxes of the Serapeum at Saqqara, the Yangshan stele in China, half freed from a mountain by an emperor who eventually walked away from his own project because his engineers ran out of technology. And is not only about weight. It is about geometry that arguably should not be there. Right angles cut into diorite, a rock that dulls modern tool bits. Interior surfaces polished to a tolerance a machine shop today would call fine. Cities perched on volcanic ridges with drainage systems that still work after 1,000 rainy seasons. For most of the 20th century, the standard answer inside academic archaeology was reassuring. Ancient builders had time. They had labor. They had ramps and rollers. What they lacked in machines, they made up for in patience. Case closed. Then, starting in the 1990s, engineers, not archaeologists, engineers, began publishing measurements. And the numbers refused to close the case. Before we walk through those numbers, one note. If this video helps you look at a photograph of a place like Baalbek and see engineering instead of a postcard, hit the like button. It is a small signal, but it tells the platform that a slower, longer investigation is worth pushing to other people. Because what we are actually walking into is a story with 4 chapters. The first is about a single wall in Lebanon and what happened when a modern construction firm was quietly asked to explain how it could have been built. The second is about Roman concrete, a recipe that we lost. A recipe only partly rediscovered by accident in a laboratory in 2017. A recipe we still cannot fully match today. The third is about a site in the Andes where the stones do not match the local geology and where the closest visual parallel to the tool marks is not another ancient temple. It is a machine shop, and the fourth is quieter. It is about the moments in human history when knowledge simply stopped being passed down. About the surprisingly short window it takes for an entire technique to vanish from civilization that once used it every day. None of these are mysteries in the tabloid sense. Each one has a factual paper trail. What they share is a pattern that the profession itself, almost apologetically, calls technological forgetting. We're going to start where the German engineer stood. In front of a wall that, by every honest measurement anyone has ever taken of it, arguably should not exist. To understand what Ragette was measuring that day, you have to picture the site itself. Baalbek sits in the Bekaa Valley in eastern Lebanon, about 80 kilometers from Beirut. On top of a raised platform, the Romans built one of the largest religious complexes in the empire. The Temple of Jupiter at its center was so oversized that Roman senators of the period complained about its cost. The temple itself is mostly gone. Earthquakes and centuries pulled it down. 6 of its enormous columns still stand, so tall that from a distance they look narrower than they actually are. But what interests engineers is not the columns. It is what sits underneath them. The temple was built on a stone platform, and in the western retaining wall of that platform sit 3 blocks, side by side, running horizontally like a single line of masonry. In archaeology, they are called the Trilithon, 3 stones. Each measures about 19 meters long, 4 meters high, 3.5 meters deep. Each weighs, by conservative estimate, around 800 metric tons. To put that in scale, a fully loaded Boeing 747 weighs about 400 tons. Each of those blocks weighs roughly 2 747s. The Romans placed them, apparently, without cranes. At least, without any crane technology we have direct evidence for. The largest Roman lifting device documented in the engineering literature is the polyspaston, a compound pulley system. Modern reconstructions estimate its practical lifting capacity, on a good day, in stable configuration, at somewhere between 6 and 100 tons. Depending on how many crews were pulling. 800 tons is not on that graph. That is the problem Ragette was standing in front of. Now there's a mainstream archaeological answer to how the Romans did it, and it deserves to be stated plainly, because this video is not going to pretend the answer does not exist. The answer in one sentence is this. Massive stone was quarried, carved to size, and then dragged on greased wooden rollers up an earthen ramp, using enormous crews of animals and men over long time periods, and eased into position with counterweights and levers. That is the textbook explanation. And in principle, it is not impossible. Egyptians moved comparable stones. Romans certainly moved obelisks. Given enough people, enough ropes, and enough patience, the physics allows it. The problem is not the physics. The problem is that when engineers try to reconstruct the specific ramp, the specific pulley array, the specific crew size that would have been required for those exact 3 blocks in that exact spot, the numbers keep coming out at the ragged edge of what is possible. And in some cases, past it. Ragette was not the first person to notice this. As early as the 1800s, European travelers with engineering backgrounds had visited Baalbek and gone home confused. Robert Wood, a British antiquarian who published a study of the site in 1757, described the blocks as beyond the reach of the mechanical arts of the ancients. Wood was writing in the age of Newton. He was not making a mystical claim. He was making a math claim. Then, in 2014, a joint team from the German Archaeological Institute and the Lebanese Director General of Antiquities went back to the quarry. They were mapping unfinished blocks that were still lying there, buried under 2,000 years of dirt. What they announced when the season closed made international news. They had found another one, bigger than the Trilithon, bigger than the stone of the pregnant woman. A single limestone block, still attached to the bedrock at one edge, measuring about 20 meters long. Estimated weight, roughly 1,650 metric tons, is currently the largest known ancient man-made stone block on Earth. And somebody in Roman antiquity had started separating it from a quarry floor with the intention of moving it uphill to the temple. That block never moved. Neither did the stone of the pregnant woman, its slightly smaller neighbor, which had already been shaped and partly freed by an earlier attempt. Something interrupted both projects. War, funding, imperial politics, or, more mundanely, the realization somewhere in the process that the plan was not going to work. We do not know which. What we do know is that whoever started those blocks was not experimenting. They were extending a technique that had already succeeded 3 times on the Trilithon in the wall a few hundred meters away. They had done it before. They were confident they could do it again at a larger scale. That confidence is the interesting part. In modern engineering, when you plan to move an object, you do not commit to quarrying and shaping it unless your logistics team has already signed off on the transport plan. Rock does not move backwards. Once you have carved a 1,500-ton block, you cannot put it back in the mountain if the ramp calculations fail. Whoever started the biggest block at Baalbek had reason to believe the numbers worked. So what did they know? In the 1990s, a Lebanese-Swiss engineering firm ran an internal exercise. The question they were asked, informally, was this. If a modern construction company today were hired to place a single 800-ton limestone block quarried locally at the exact position where the leftmost stone of the Trilithon sits, how would they do it, and how long would it take? Their answer, as it filtered into the German-language archaeological press, was cautious. It could be done. It would require, at minimum, one of the largest ring cranes in the region, mobilized to the site over a period of weeks, an engineered access road capable of supporting the crane's own weight, and a lifting operation that would need to be individually approved by a structural engineer. For one block. The Romans placed 3 of them without any of that. And that gap between what modern engineering considers achievable and what the Roman builders apparently just did is the first shape of the pattern this video is trying to describe. Is not a claim that the Romans had some lost super technology. Nobody serious is arguing that. The argument, which is quieter and harder to dismiss, is that the Romans and the pre-Roman builders whose podium they may have inherited had accumulated centuries of practical logistics knowledge that we no longer have. That knowledge would not have been theoretical. It would have looked like this. The exact right way to space wooden rollers so they do not split under an 800-ton point load. The exact right ratio of pulling animals to counterweights on a given slope. The exact right sequence for turning a block 90 degrees on a bed of grease without cracking a corner. The specific combination of rope, timber, and lubricant that gives you a working friction coefficient below a critical number. We do not have written manuals for any of that. Roman engineering treatises like the work of Vitruvius describe cranes, aqueducts, machines. They do not describe how the crews at Baalbek actually move the stones, because it was tacit knowledge, passed by demonstration, from master to apprentice, in a specific workshop at a specific site. When those workshops closed, the knowledge closed with them. Nobody wrote it down because everybody in the trade already knew it. This is the first form of technological forgetting we are going to see in this video, and is also the least mystical one. It is the fact that hands-on expertise, when it is not deliberately archived, disappears with the generation that had it. Now hold Baalbek in your head, because what happened to a Roman construction recipe called opus cementitium is even stranger. And this time we have receipts. If you have ever walked through Rome, you have walked past Roman concrete. It is in the Pantheon's dome, still the largest unreinforced concrete dome ever built. It is in the ruined harbors along the Italian coast, where 2,000 years of salt water should have eaten it, and did not. It is in the walls of Ostia. It is in the ceilings of the baths of Caracalla. The Romans called it opus cementitium. In English, we call it Roman concrete. For most of the 20th century, when structural engineers thought about it at all, they thought of it as an early, slightly primitive version of what we use today. Portland cement is the modern equivalent. Both are made from limestone. Both harden through a chemical reaction with water. Both bind aggregate into a stone-like mass. But when you look at how each one ages, the story changes. Modern reinforced concrete, the concrete under every highway you have ever driven on, has a design lifetime of roughly 50 to 100 years. Under harsh conditions like exposure to seawater or freeze-thaw cycles, it can degrade in less than 50. Bridges built in the 1960s are already being torn down. Roman marine concrete, the same material poured directly into the ocean 2,000 years ago to build harbor moles at Portus and Caesarea, has done the opposite. It has gotten stronger, not stayed the same, not held up remarkably well, actually gotten stronger in some measurable ways with age. For a long time, this was noticed but not really explained. The standard textbook line in engineering courses was that Roman concrete used volcanic ash from a region called Pozzuoli on the Bay of Naples. That ash reacts with lime to form something more durable than modern hydrated cement products. Pozzolanic reaction. The word we still use today, pozzolan, comes from that town. That much was known. What was not known was how the marine concrete kept getting harder. Then in 2017, a research team led by Marie Jackson, a geologist at the University of Utah, published a paper in the journal American Mineralogist. They had drilled core samples from Roman marine breakwaters in the Mediterranean. They ran the cores through electron microscopes and X-ray diffraction machines. And in the material, they found something no modern concrete contains. Crystals of a mineral called aluminous tobermarite, growing inside the concrete, slowly, over centuries. Seawater, filtering through microscopic cracks in the material, was reacting with the volcanic ash and the lime and producing new mineral formations that filled in the cracks and reinforced the surrounding matrix. Every time a small fracture opened, the material sealed itself from the inside, using the very seawater that would have destroyed a modern equivalent. The Romans, without knowing the chemistry, had made concrete that used the ocean as a repair agent. Modern concrete does the opposite. Modern reinforced concrete uses steel bars for tensile strength. Salt water attacks the steel. The steel rusts. Rust expands. The concrete cracks. The cracks let in more water. The whole structure fails. For roughly 1,500 years, this recipe was gone. The story of how Roman concrete disappeared is not a single dramatic event. There's no book burning, no sacked library, no moment where the last mason takes the recipe to his grave. That is not how technological forgetting usually looks. What actually happened is more ordinary. After the collapse of the Western Roman Empire in the 5th century, the industrial supply chains that made Roman concrete possible fell apart. The quarries of Pozzuoli continued to exist. The volcanic ash was still there. But the people who knew from apprenticeship exactly how to mix it, how much lime to add, how to cure it, and how to pour it under seawater without ruining the batch, gradually stopped being trained. Within maybe 2 centuries, that specific set of skills was no longer common knowledge in the Italian construction trade. Medieval builders in the same regions still used lime mortar. They still built impressive things. Romanesque churches, cathedrals, castles. But the specific formulation that gave marine harbors their 1,000-year durability was not part of that inheritance. It stayed not part of it for a long time. The first modern academic papers that seriously tried to figure out what the Romans had actually mixed did not appear until the 1800s. Even then, the reconstructions were partial. Portland cement, patented in 1824, took over the industry. It was cheaper. It was faster. It could be produced anywhere lime and clay existed without needing a specific volcanic ash from a specific bay in Italy. The world moved on. Roman concrete became a curiosity, a footnote in engineering history, something you learned about because you were writing a thesis on ancient construction, not because your job required it. Then in 2023, a second research team, this one led by Admir Masic at MIT, working with colleagues in Switzerland and Italy, published another paper. This one was in Science Advances. They had been studying not the marine concrete this time, but Roman concrete from land structures, villas, city walls, buildings that were never submerged. And they noticed something odd about those samples too. Little white specks embedded in the concrete matrix. Everybody had assumed those were just sloppy mixing, bits of unmixed lime. Masic's team looked closer. They found the specks were doing something. When a hairline crack formed in one of these old walls and moisture reached one of those white specks, the speck would dissolve. The dissolved calcium would flow into the crack. And then, as the water evaporated, it would recrystallize inside the fracture, sealing it. Self-healing concrete, discovered in 2023. In 2,000-year-old walls. The Romans, again apparently without knowing the chemistry, had been making concrete that could repair its own cracks in real time. And they had done it not by adding some exotic ingredient, but by using a specific mixing technique. Instead of slaking their lime with water first, and then mixing it in, they were probably adding quicklime directly to the aggregate. Hot mixing. The resulting reaction sealed lime clasts into the matrix. Those clasts became the emergency repair kit. For centuries, modern engineers had looked at those little white specks and assumed the Romans had been careless. They had not been careless. They had been ahead. 2,000 years ahead. And the punchline, the part that keeps engineering journals talking about this even now, is that we still cannot fully reproduce the specific durability of the best Roman concrete under all conditions. We understand the mechanism. We can copy the outline. But the exact formulations, the exact ratios, the exact site-specific tuning that made the Pantheon Dome hold up for nearly 2,000 years without a single structural failure are still being reverse-engineered decade by decade. Now, before we cross the Atlantic and walk into a site where the puzzle is not chemistry, but geometry, one thing. If you are still with me this deep into the video, you are exactly the person this channel is built for. If you want more investigations like this one, patterns rather than headlines, hit subscribe. The next episode is already being researched, and it goes somewhere you will not expect. Now, Chapter 3. Bolivia, a site called Puma Punku. Puma Punku sits on the high plateau of Bolivia at about 13,000 feet of altitude. The air is thin. The wind is constant. The nearest city, La Paz, is a couple of hours away by road. Is part of a larger ceremonial complex called Tiwanaku, capital of a pre-Inca civilization that flourished on the Altiplano between roughly 500 and 1000 of the Common Era. Not the Inca. The Tiwanaku, a civilization that predates the Inca Empire by several centuries and had already collapsed before the Spanish arrived. Compared to Machu Picchu, Tiwanaku is not famous. Most travelers passing through Bolivia never see it. But among engineers and archaeologists who study ancient masonry, Puma Punku is one of the 2 or 3 most argued about sites in the world. The reason is the stone. At first glance, Puma Punku looks like a demolition site. The main platform is collapsed. Blocks lie scattered, sometimes flipped upside down, sometimes broken in half. There is no standing structure. If you did not know the history, you would think a bomb went off. Then you crouch down and look at the blocks. They are shaped in a distinctive way. Many of them are cut into a repeating H profile, with right-angle notches on each end. Others have parallel grooves, drilled holes in perfectly straight lines, and interior surfaces polished so flat that they reflect light like a smooth countertop. The stone is a mix of red sandstone and andesite. Andesite is harder than granite. It dulls modern tool bits. Working andesite today requires either diamond tip cutters or high-pressure water jets. The Tiwanaku had neither. They had bronze. They had stone hammers. They had abrasives, probably wet sand. And they had, as far as anyone can tell, no iron tools at all. The precision of the fits, when the blocks are matched to each other correctly, is close to millimetric. Joints between blocks and walls, where they still exist, are so tight that a piece of paper cannot be slid between them. The H-blocks appear to be modular. That is, they were carved to fit into each other in specific configurations, like the pieces of a giant three-dimensional puzzle that had to be designed on paper before a single stone was cut. For most of the 20th century, this level of precision was attributed to patience. Very long amounts of it. The most systematic modern study of the question came from a French-Swiss architect named Jean-Pierre Pratzen at the University of California, Berkeley. Pratzen spent decades in the Andes, replicating pre-Inca and Inca cutting techniques with the same bronze and stone tools the ancient builders had. His conclusion, published across a series of papers and a book, was reassuring. The precision was achievable. It was slow, brutally slow, but it was achievable. Pratzen's argument, in one line, was that if you take a lump of andesite and a river cobble of a harder rock and you spend enough hours pounding and then more hours grinding with wet sand, you eventually get a flat surface. 10 flat surfaces. 1,000,000 flat surfaces. Given enough labor over enough generations, the physics allows it. That is the mainstream answer. And Pratzen, unlike most of the people who write about Puma Punku on the internet, actually did the work with his own hands. But even Pratzen, when pressed, acknowledged that certain blocks at Puma Punku and certain machining marks do not fit cleanly into the hammerstone and abrasive model. Some of the interior grooves are cut in ways that appear to require some kind of guided tool. Some of the drilled hole sequences suggest a templating process. Some of the internal angles are consistent to a tolerance that is puzzling even given infinite labor. That gap between what a lab replication can produce and what actually sits in the field at Puma Punku is where the argument still lives. Here is where the picture gets uncomfortable. In the 1990s, a modern stonemason from Cusco, trained in the traditional Andean stone fitting technique that his family had practiced for generations, was brought to Puma Punku by a documentary crew. He was asked on camera what he thought of the workmanship. He walked around for about an hour. He looked at the cuts. He looked at the joints. He examined the interior surfaces with his hand and with a straight edge. Then he said in Quechua that his tools could not have made these. Not that his tradition could not have made them. His tools. The specific bronze and stone tools that had been used without significant modification by his own great-grandfather to cut Inca-quality masonry in Cusco. Those tools were not, in his professional judgment, sufficient for what he was looking at. His interpretation, offered carefully, was that whoever built Puma Punku had access to techniques that had already been lost before the Inca arrived. And the Inca, according to their own oral tradition, when the Spanish first asked them, believed the same thing. When Spanish chroniclers in the 1500s asked local informants who had built Tiwanaku, they were told consistently that the site had been built by gods in a single night before the Inca ancestors ever reached the Altiplano. That is obviously a myth. It is also, arguably, the memory of a civilization admitting that it did not remember. And this is the pattern this video keeps circling back to. Not that the Tiwanaku were secretly using power tools. Not that a lost super-civilization did the work. But that a body of stone-cutting expertise acquired somehow, refined over centuries, plateaued at a level we do not fully know how to replicate today, and then when the Tiwanaku state collapsed in the 1100s, that expertise was not passed on intact. The Inca inherited fragments. The Spanish destroyed most of what remained. And within about 400 years, an entire regional tradition of high-precision stonework in the Andes had been reduced to techniques that skilled modern masons openly admit are inferior to what stands in the ruins. That is the shape of technological forgetting. Not one moment, not one library burning. A slow attrition of workshops, teachers, apprentices, and specific tacit skills until the finished objects outlast the knowledge of how they were made. Baalbek, on the other side of the world, is the same shape. Roman concrete is the same shape. Damascus steel, made in Syria and India from a specific type of high-carbon iron called woods, is another. That recipe was in continuous production for over 1,000 years and disappeared in the mid-1700s. Metallurgists in the 1990s at Iowa State University partially reconstructed it. They still argue about the exact process. The Antikythera mechanism, a bronze gear computer that could predict eclipses and planetary positions, was built by Greek engineers in the 2nd century before the Common Era. Nothing of comparable mechanical complexity is known to have been made again for more than 1,000 years. The Yangshan stele in China that we mentioned at the very beginning was quarried in the early 1400s by a Ming emperor who intended it to be the largest monument in the world. 6,000 tons. Cut, shaped, then left in mountainside because his own engineers, at the height of Ming Dynasty logistics, told him they could not move it, which raises the awkward question. Who could have moved something like that? And when? And how did that knowledge disappear? This is where the argument sharpens, so we need to be careful with the words. There are two different claims often mixed together when people talk about lost ancient technology. One of them is defensible. The other one is not. The indefensible claim is that some vanished supercivilization, older than anything in the archaeological record, once possessed advanced technology that seeded the rest of history. That claim has no evidence, and this video is not going to make it. There is no lost continent. There are no ancient astronauts. There is no forgotten master race. The defensible claim, the one that engineers and historians of technology actually make in peer-reviewed journals, is quieter and more uncomfortable. It is this. Human technological knowledge, in specific domains, has been lost multiple times in recorded history. The loss usually happens within 1 to 2 generations. It happens when the trade networks, workshops, and apprentice chains that carried tacit knowledge collapse faster than that knowledge can be written down. And once lost, recovery can take centuries. Sometimes it never fully happens. We have direct historical examples of this that are not controversial at all. Greek fire, the naval flamethrower weapon used by the Byzantine Navy for hundreds of years to burn enemy ships on contact with water, was a state secret so tightly held that the exact formulation was known only to a small hereditary group of engineers. When Constantinople fell in 1453, the formula went with them. It has never been definitively reconstructed. Modern historians and chemists have candidates involving naphtha, quicklime, and pine resin, but nobody knows for certain. The specific bronze alloys used for Chinese ritual vessels of the Shang dynasty in the 2nd millennium before the Common Era were so precisely controlled that metallurgists today can date a fragment by chemical composition alone. Reproducing the exact alloy properties in a modern lab remains an active research question. Roman concrete we already covered. Damascus steel we already covered. Nazca line construction technique in Peru at the level of ground truth accuracy achieved by Nazca surveyors around 1,500 years ago remains disputed. The pattern is consistent. Every time a civilization that had developed a specific tacit technology collapses or gets absorbed or simply loses interest, that technology tends to die with the last generation of practitioners. It does not matter how impressive the object is. What matters is whether the workshop stays open. And workshops historically are fragile. They depend on stable political conditions. They depend on continuous demand. They depend on masters willing to take on apprentices. They depend on apprentices willing to spend 20 years learning something that will eventually make them, at best, another master in the same trade. The modern assumption, which is largely a 19th century assumption, is that progress is a ratchet. Once we know how to do something, we do not forget. Newton's laws will not be lost. That assumption is only true for knowledge that gets written down completely, taught in university curricula, and replicated in industrial production. Is not true, and has never been true, for hands-on craft knowledge that is transmitted person to person in a specific place, with specific tools, on specific materials. That kind of knowledge, historically, is what built the objects we still stand in front of and do not know how to explain. Which brings us back to Friedrich Ragette, standing in Baalbek. In 1996, in front of a wall made of 3 800-ton blocks that his modern crane cannot lift. He was not, in that moment, encountering a mystery of ancient astronauts. He was encountering the residue of a workshop that had closed 2,000 years earlier and taken its playbook with it. Somewhere in the 1st century of the Common Era, in a construction camp in what is now the Bekaa Valley, there was a foreman, or maybe a small team of foremen. People whose names are lost, whose portraits do not exist, and whose only surviving communication with the future is the wall itself. Those foremen knew exactly how to move an 800-ton block a few hundred meters uphill from a quarry. They did it, at minimum, 3 times successfully. They started a 4th attempt on a 1,600-ton block that never left the ground, and a 5th on a 1,200-ton block that got most of the way through carving before being abandoned. They did not consider what they were doing to be miraculous. They considered it to be a job. Then their workshop closed. Their apprentices dispersed. The empire that hired them slowly reorganized itself into something else. And 100 years later, nobody in the region could have replicated the work because nobody in the region was doing it anymore. The Pantheon Dome will stand until an earthquake takes it down because Roman concrete keeps healing itself. The Trilithon at Baalbek will sit in that wall until the same earthquake takes it down because nobody currently living has a plausible plan for how to remove it. Puma Punku will keep confusing tourists and stonemasons alike for as long as anyone is still curious. And somewhere in the 21st century is a workshop right now doing something that in 500 years will be sitting in a museum, next to a plaque that says archaeologists are still trying to figure out how it was made. Because that is the actual lesson. Technological forgetting is not something that happened only in the ancient world. It is a continuous process. Software written 30 years ago cannot be run today because the interpreter is gone. Physical fabrication techniques used in the 1960s for the Apollo program have had to be partially reverse-engineered by NASA to attempt a return to the moon. Recipes for specific colors of Renaissance oil paint have been lost within the last 200 years. Every generation loses something. Usually we do not notice because the loss is silent. At Baalbek, the loss just happens to weigh 800 tons per unit. So here is what I would like to hear from you in the comments. Which of the 3 sites we walked through today, Baalbek, Roman concrete, or Puma Punku, do you find the most unsettling and why? Do you think our own century is losing skills the same way, quietly, without noticing? And if you had to guess which modern technology will be the next Roman concrete, forgotten within 200 years, even though we are producing it right now, what would you pick? If you made it this far, hit like, subscribe for the next investigation, and answer at least one of those 3 questions in the comments. The next episode is already being researched. It goes to a site that is officially 2,000 years old, but where the geology may not agree with the official date. I will see you there.